Okay, this is the introduction to 6-1 on just polygons. So we're looking at a closed-sided shape, a many-sided closed figure made up of straight line segments that don't intersect. So a polygon is a many-sided figure. That's where the word poly comes in. Gon is figure, made up of straight line segments that don't intersect. So look at the examples down below. You can see here we have an intersection, so that is not a polygon. We see here there is not a straight line segment, so that is not a polygon. And the other three are closed figures made up of straight line segments, so these are all yeses. Here, here, and here. That's what a polygon is. Polygons are either convex or concave. The way I think about it is concave is like a cave, it goes in. So like this one right here is concave, it goes in at some point, whereas these two here and here are convex. Or you can think of it as if you're like, it's like blowing up a balloon. If you had a polygon-shaped balloon and you blew into one of these corners, it kind of pops out. That's convex. Official definition here is convex is no line that contains a side of the polygon goes through the interior itself. So for example, on this one right here, the one that is actually concave, is you can see that I drew this blue line segment, an extension of one of the segments of that polygon, and it does go through. It is a line that goes through a side of the interior of the polygon. So that one is concave because there is a line that contains a side of the polygon that goes through the interior of itself. Whereas here, I can draw all the extended line segments, and none of those blue line segments goes through the inside of the figure. So that's how we're going to handle it. Concave is not convex, and convex is, it passes that test where I draw the extension of each line. Oops. Draw the extension of each line here, and none of those extensions go through the interior of the shape. Let's try the test on this guy right here. Start going through here. Oh, by the second one, you can see that it goes through the interior of the shape. So this one is concave. And the other one here passes the test. All these extended line segments, none of them go through, so that one is convex. All right. When it comes to polygons, we're going to be studying in this chapter primarily four-sided polygons, but we need to know the names of the different polygons so that when you're asked to find the area or angle measurements inside the polygon, you'll know what they're talking about. So number of sides 3, that is your triangle. Number of sides, when you have 4 sides, it's a quadrilateral. 5 sides is a pentagon. And you may already know these. You don't need to write it down if you know these already. 6-sided is hexagon. These are in your long-term memory. You're probably fine. 7-sided is heptagon. It's H-E-P-T-A-G-O-N. 8-sided is octagon. That's our stop sign. 9-sided is nonagon. 10-sided is decagon. 12-sided is dodecagon. So those are the ones you should know. Unagon is 11. That wasn't in there. If you want to know 11 sides of unagon. And then like if you get to 13, 14, 15 sides, we just call it a 15-gon, 14-gon, 13-gon, or n-gon. So those are our polynomials. Challenge for the day is try drawing a polynomial with anything more than 8 sides. It's hard. So 9, 10, 11, 12. It starts looking like a circle. So that's your challenge for today. All right, so special classifications of polygons. We have equilateral ones, all sides equal. Equiangular ones are all angles equal. And regular polygons have all sides and all angles equal. So for example, this first one, example 3, has all 4 sides marked as equal, so that is equilateral. We don't know on the angles, so just the sides are equal, it's equilateral. This next one has sides and angles marked as equal, so this is regular. The next one is none of the above, looks like Pac-Man. There are no sides equal, no angles equal. And the last one has neither sides nor angles equal, so this is none. Another definition here, a diagonal is a line segment that connects two non-adjacent sides, such as this or this. Those are diagonals of a polygon. So we're going to use the idea of diagonals of a polygon. Let's take let's start with our 4-sided figure here. There's a 4-sided polygon. And with those polygons, we want to start thinking about how many triangles make up a 4-sided and then a 5-sided and 6-sided polygon. So here I have, if I draw my one diagonal in, I have 1, 2 triangles. If I go from that to a pentagon, here's the pentagon. From one vertex here, I can draw 2 connecting diagonals, giving me 1, 2, 3 triangles. So a 4-sided shape has 2 triangles. 5-sided shape has 3 triangles. You might be able to guess at this point what a 6-sided shape has. I draw all the diagonals from one vertex, so all the diagonals, remember diagonals are drawn to non-adjacent vertices, so we don't draw one to here or to here, but to the other 3 we do. That creates 1, 2, 3, 4 triangles. 6-sided shape has 4. 5-sided shape has 3, and a 4-sided shape has 2. So you should be noticing that there are 2 less than the number of sides in terms of how many triangles you have in each polygon. That's true for any size polygon. So with that knowledge, combined with the fact that in any triangle, all 3 angles in each of these triangles add up to 180, you can find the sum of the measures of the interior angles of any n-gon. It's always the number of sides, that's the n minus 2 here, times 180. The 180 comes from the fact that in any triangle, the sum of the interior angles is 180. So what we are doing is triangulating these shapes and then counting the number of triangles and multiplying by 180. You probably don't want to draw anything, though, bigger than an octagon. If you tried it, it's hard. So if you know you have a 14-gon, then it's just 14 minus 2, or 12 times 180, and that tells you what all the angles add up to. So we're going to use that fact on these problems down here. So on example 4, this is a quadrilateral. We know it's 4 minus 2 times 180, or 2 times 180, which is 360 degrees, is what all 4 angles add up to. So we can write an equation that says x plus 2x plus 80 plus 70 has to equal 360 degrees. Combine like terms and solve for x. So subtract the 150 over, you got 3x equals 210, and x equals 70. So if x equals 70 degrees, then 2x, that would be 140 degrees. So we found the missing angles Q and R. So this is our heptagon. Heptagon is 7 sides. So we have 7 minus 2 times 180, or 5 times 180. This is only asking for the sum of all the inside angles. So we go 5 times 180, that's 900 degrees, and that's all they're asking for. If they said, okay, each of them are equal, it's a regular heptagon, you would divide by 7 to get each interior angle. All right, so that's the sum of the interior angles of any polygon can be found using this formula right here, n minus 2 times 180. When it comes to the exterior angles of a polygon, let's go ahead and draw those first. If you make an extension here for each one of these, that's an exterior angle, that's an exterior angle, and that's an exterior angle. And you can go all the way around. And as you go all the way around, even on this crazy heptagon up here, what you'll notice is that you would make one full turn if you kind of picture yourself walking along those line segments, turning through angle 1, and then angle 2, and then angle 3, and then angle 4, 5, 6, and 7. You end up back facing where you were before you turned through angle 1. And so you've made one full revolution, which is 360 degrees. And as a matter of fact, I could do that for any size polygon. Here I am with my hexagon here. There's 1, 2, 3, 4, 5, 6, and I'm back to where I started. So find the measure of n exterior. Well, first of all, the sum of all of them, or sum of them, is 360 degrees. If you want to find one of them, you just got to take 360 and divide by n to find one. What is n? N is the measure, or the number of sides we have here. So we have 360 over 6, which is 60 degrees. So any of these around here is going to be 60 degrees. If I change the shape and it was a pentagon instead, it's 360 divided by 5, which is 72 degrees for each angle out here. So this would be 72, 72, 72. You just keep going around here. That's it for the exterior angle. So hope this helps.